Let me briefly mention about the basics of probability before you conduct the simulation study. So, as you know, sample space is a set of all possible outcomes. So, if we have a die with the 6 numbers, and sample space will include all 6 possible numbers from 1 to 6. And probability space or probability model is a sample space with an assignment PW, probability value, for every W, okay, including sample space. And as you know, probability always between 0 and 1, and then summation of the all possible probability or probabilities of all outcome will be 1, right? So if you think about the die again, and then it will, if it has an even surface, and definitely will the probability of each number will be 1 over 6. And event A is any subset of omega, okay? So in other words, subset of sample space. So if there is an event A, there is a probability for event A, and you have to consider all the probability values associated with this event A. Okay, if you die alone, and then definitely if you roll a die and then die, and let's say the value outcome is less than 4, and then the probability value, each probability value will be summation of probabilities from 1 to 3, right? So in other words, 1 over 6 plus 1 over 6 plus 1 over 6. So basically, the conclusion will be 3 over 6. So it will be 50%, or 0.5 will be the probability value of this event A, right? There are 2 types of random variables, and first one is discrete random variable, and next one is a continuous random variable. And usually discrete random variable has a certain number, for example, integer number, like x1, x2, xi, and so on. And we use a probability mass function to describe the discrete random variable, as you know. And here's an example of the PMF, okay, or probability mass function. And in this case, we have 4 different, x can have 4 different values, such as 2, 4, 6, 10, and we have 4 probability values for each x, these 4 x values, so 0.2, 0.2, 0.4, 0.2, okay? So if this random variable x equal to 2, then definitely the probability, each probability will be 0.2, okay? And in order to illustrate this distribution, we widely use cumulative distribution functions such as the CDF, and continuous random variable also use a CDF, but shape is slightly different. Basically, in order to have a CDF for this discrete random variable, we can have this kind of shape shown here. And as you know, we have 4 different values for x, right? 2, 4, 6, 10, and each case has the associated probability value, such as 0.2 and 0.2, 0.4, 0.2, right? So in CDF, you have to add the probability value to the previous case. In other words, you have to accumulate the probability value, okay, over the x. So 0.2, start from 0.2 here, and then add another 0.2 when x equals 4, and when x equals 6, you have to add another 0.4, right, here, so that you will get 0.8 as a CDF when x equals 4 and 6. And then last one is when x equals 10, and definitely you will have the probability value will be 1, right? So as you can see, this one also meet the definition of probability, right? As I mentioned before, I already mentioned that probability value is always between 0 and 1, and then summation of all probabilities will be 1, right? So this follow that definition, of course. And continuous random variable has a slight different shape. Of course, in this case, it can have any real number, okay? And because it can have any real number, you have to use the probability density function to illustrate the probability for the certain interval or certain range. So that's why the shape of the PDF is like this, and CDF also use the integration function here, okay? So if you look at this PDF actually for the continuous random variable, and as you can see, X has a range. Okay, so in each range actually you can calculate the probability value, and CDF will have a continuous shape, and at the end CDF will become what? 1, right, according to the definition of probability. Okay, so and then also we have 3 different types of concept, right, associated the probability theory. And as you know, joint probability is what? So let's say we have this kind of the space, including how many squares we have, including 15 squares. Okay, and over the 15 squares, actually joint probability is associated to random variables when x equals to xi and y equals to yj. So xy, let's say this area, okay, has is related to the xi, and then this area, this second law, is associated the value of yj. Okay, and joint probability, in other words, of x of given y under given y and x will be nij over n, because only this square is what is related to the xi as well as yj, right? So this value over n will give you the joint probability, and marginal probability is so from the joint probability, you can calculate the marginal probability by adding the all other variables. For example, so when you want to calculate the marginal probability when x equals to xi, and then you need to add all the probabilities, right, related to xi, right? So however, yj can have 3 different values, right? So in order to get in order to get the marginal probability, and basically you have to consider this entire area, in other words ci, okay? So if you divide this value ci by n, and definitely you can get the marginal probability, in other words probability when x equals to xi. Good. And conditional probability, so conditional probability actually is like this. So probability when y equals to yj, okay, conditioning on x when x conditioning on xi. So in order to do that, you have to consider only this area, okay, only this area associated to xi, okay, and then based on this area we want to know the probability of the yij, probability of yj, okay, yj. So in order to calculate that probability, basically you need to divide this nij by ci, right? So if you reuse the marginal probability as well as joint probability in this equation, and then definitely we can get the same result. Okay, because I just reviewed the basics of probability theory, so you already knew this kind of concept. If you don't know, yeah, please review the probability theory or statistics book. Okay, expectation and variance. Yes, so this equation actually give you the expectation for the discrete random variable and then continuous random variable, right? And of course, so if you have constant, multiplied by the random variable, and basically you can take this out of the ex function, right? Also, if you add constant, and then also you can take this out, right, from this function, something like this. And also the square of the ex is different from the expectation of the x square, so you need to know this, right? And based on this, basically you can calculate the variance, right? And here is the equation to calculate the variance, and variance is a can be represented as like this, right, as this function. And only different and however, in variance, actually you cannot take this out, right? So this is constant, right? So constant has no variance. Variance equal to 0. So that's why you have to ignore this constant term. And however, if there's a constant multiplied by the random variable, and you can take this out, right? But you have to scale it, right? So that's the theory associated the variance property. And covariance is given by this equation. So basically, if x and y are related to each other, so we use a covariance to check the independence between the x and y, two variables. So if x and y is independent, then what? This covariance becomes 0. Okay? Why? Because if x and y are independent, and then this exy will be ex multiplied by ey, so this value will be cancelled out, right? So these two terms will be cancelled out, so that's why you will get 0, right? So if covariance is 0, and then two variables are independent, right? Also, conditional probability between two variables are also, will have this kind of relationship, because the probability between joint probability will be px times py, right? That's why. Okay. All right. So far we just reviewed the basics of the probability theory, basically, very quickly. And today, actually, I want to discuss queuing theory a little bit to give you the better understanding on the system. Okay, so let's look at the queuing system, consisting of the arrival process, queue, and the service process. Okay, and I think that you already knew about one of the queuing system. Actually, we have considered the simple processing system, right, in previous chapters, right, such as drilling center. Hopefully you can remember this. We have drilling center, we have drilling center having one drill press, right, and one queue, FIFO queue, first in, first out queue. And there is a part arrival and part departure. Yes, part departure. Yes, and then we have a service process, which is drill process, and then I already mentioned that we have FIFO queue, right? Queue is here. If I just mention queue, and usually we assume that it has a first in, first out rule, okay? Discipline. All right, so let's look at this one. So whenever a part enters the system, and then the first part will be solved by the drill press, and others will be waiting, right, for their service. And then once the process is ended, and then the part will leave the system. Good, very easy. Yes, so in queuing theory, traditionally we use the queuing theory a lot to understand the performance, especially to estimate the performance of this kind of system, right? And I think in communication area, actually, or network area, network field, I still use the queuing theory a lot, right? To estimate the performance of the computing network or communication network and so on. So, right. So queuing theory is basically widely used to provide models for forecasting forecasting behaviors of systems subject to random demand. Okay, so basically there are three common factors causing the randomness and in the system. So first one is a arrival process, and next one is a service process. Okay, and then last component is actually the not basically three, but performance is basically the process. Okay, the number of server, and then four, yes, the queue. Okay, the discipline associated with queue. So basically three is our library process, service process, and then queue. Okay, right. And as I mentioned before, this is a very popular analytical method actually, because of its computational efficiency and prediction accuracy. And once you have once you can actually define your system as one of the queuing model, and basically you can mathematically calculate the performance or estimate the performance of system. Also, you can understand what's happening in the system over the time. Okay, so that's a very good thing. So, and that's some equation, so computer easily can calculate quickly, very quickly calculate the performance or estimate the performance. Okay, that's a good thing. However, it can be only applied to the relatively simple system, like a 1Q or 10Q and so on, but or one server, two server with the same rule, or and so on. Okay. However, as you know, the in-VR system actually has a multiple servers with different disciplines and queuing disciplines and service times, and those are so complicated, right? So that's why you can, by understanding the queuing theory, and basically you can actually easily understand the theory using the simulation, because simulation can be used to model the complex system, right? So let's start from the simple system with queuing theory. And application of the queuing theory is a very wide. I already mentioned several things, but yes, traffic control of the communication network or scheduling of a manufacturing system and so on. Okay. And let's look at the candles notation quickly. So here is a candles notation, and I will give you the definition here. So A means arrival process, and first one is arrival process, and next item is service process, and third item is number of service servers, and fourth one is the capacity of the system, and fifth one is the population size, and sixth one, last one, is the service discipline. Okay, so for example, here is a MM1 on MM1, and then unlimited 5-port model, and usually this is known as just MM1 queuing model. Okay, yeah, usually we ignore this unlimited symbol from the original candles notation. Okay, and M means Markovian process, such as a Poisson process or exponential distribution. Okay, so this is our process. If you look, when you look at this model, and this is the first is M, so which means our level process is following the Poisson's process, and as you know, the interval time between the entities following the Poisson process is following the exponential distribution, right? That's why we use N and M, right? And here is another M, exponential distribution. Okay, right. And then this is a shape of exponential distribution, and this is a discipline using the Q, right? So FIFO, first in, first out, right? I already mentioned this right before. Where are you? Here, right? So FIFO Q. Now another discipline, instead of FIFO, yes, we have a LIFO, right? Last in, first out, something like that. Okay, so we have really several actually disciplines for the queuing model. Okay, but don't worry too much about it, because this is a simulation class, so I'm not going I'm not ask you too much detail on this queuing theory. And let me explain the several nomenclatures of the symbols. And here NT is which means is a number of customers in the system at time t. NT is the number of customers. And then this is a PN. T is a probability that n customers are in the system at time t. So n probability. P is a probability, n is number of customers in the system, and then t is the time. Okay. And if you run the simulation, run the simulation model really long time, or run the disk queuing model really long time, and then what? And then you can ignore the time, right? Because this probability value will be converged to the certain value. So Pn means long run probability that there will be exactly n customers in the system. So T will be sent to unlimited. So okay, so this is a long run probability, and this is the probability at time t. And mu n is the average service rate. Okay, for our system when n customers are in the system. Good. And lambda n is also similar, but arrival rate. This is a service rate, and this is arrival rate. Okay, and arrival rate of entering customer when n customers are in the system. Very simple, right? And if you ignore the n, that means long run average arrival rate of entering customer. Okay, so in this case, yes, we consider the unlimited number of customers from 0 to unlimited. Okay, so long run average arrival rate. So given by this equation, okay? And this is what? This is a long run probability, right? With the n customer. Yep. So fundamental quantities of interest in queuing theory. First one, average number of customers in the system. So average number of customers in the system is L, and the average number of customers is server and Q, right? So if you know how many people in the server and in average, and if you know how many people in the queue in average, and definitely if you add these two numbers, and you can get the average number of customers in the system, right? That's a L. And yes, it's too fast, right? Once again, L is the long run average number of customers in the system. LQ is the long run average number of customers waiting in queue. LS is the long run average number of customers in service, okay, or in server. Yeah. And next one, average time the customer spend in the system. Okay, also known as time in system. Yes. All right. So average time. So in service, in queue, right, will give the same result of W. So W, again, the long run average amount time a customer spend in the system, and WQ is a long run average amount of time a customer spend in the queue. Long run average amount of time a customer spend in the server will be WS. So WQ summation between WQ and WS will give you W. Okay. In other words, if you know how much time your customer has to spend both component, right? Queue and also service, right? Queue and service. So if you know the waiting time for each component, and then by adding these two times, actually you can get the total time in the system, right? So that's how you calculate the average time the customer spend in the system. Okay, let's talk about the little formula showing the relationship between the waiting time and not waiting time, time in service, and also number of customers in the server. Okay, so this formula shows the relationship between L and W. And here's a proof. Let's say we have an equation for the L. Okay, so basically we have let's say we have a system, and then you want to run the system for 20 minutes. Okay, and this graph show you the number of customers at time t. Okay, so over the 20 minutes, actually in 20 minutes, you can see the number of customers in the service. So from 0 and there is no customer, and however one customer enter the system and then leave the system, and another one another customer enter the system, and another one, second one, is also enter the system, and so on. So you have this kind of, let's say you have this kind of graph. Okay, to understand this kind of graph, to understand, and then this one actually help you understand how many customers in the system over the time, right? And based on this, actually you can calculate this graph. You can calculate the number of customers, right? Average number of customers in the system, right? Over the time. So in order to get this shaded area, and basically you have to get the integration of the nt, right? And then this value can be divided by larger t, which is 20 minutes, right? So that you can get the value of L. So this part is L, okay? And you can play with this one actually to prove the relationship between L and W. How? And let's use n here, and then multiply n here, and then let's split this. Where is a pen? Let me use a pen. And let's split this, okay, into two terms by using n. Okay, this is just technique. So because these two are cancelled out, and eventually, so this one, the term right on the right hand side is exactly the same as the term right on the left hand side, right? So let's change the shape a little bit like this, and then based on that you can draw this kind of graph, right? In other words, number of customers. Okay, so basically, in other words, there is several number of customers, right? So 0 customer, 1 customer, and 2 customer, and so on, right? This is number of customer, and this is what? So time in the service, or time in system, right? Of each customer, first customer, second customers, and so on, right? So especially when system has 1 customer, 2 customer, 3 customer, and so on. So this one give you the W, right? So that's how you get the W. And yes, so in order to get the shaded area of this graph, basically you need to add all the Tn, right? From T1 to actually Tn, capital N. So, and then divide this value by number of customer in the system, which is N, large N, right? Total cases, actually total cases, whole cases, guys. So consider the whole cases of customers. So basically, which is large N, right? So that's how you get the W value, right? And then, so basically this can be split into the two terms like this, right? And as you know, this one is give you what? Give you W, and this term give you L, right? And this term is what? Under the given amount of time, and there are n number of customers, right? By divide this large N, capital N, by capital T, and you can get the what? Lambda, right? Arrival rate over the time. How many customers can enter the system over the time, right? So this is a lambda. Got it? That's how you prove the Little's formula. Okay, and you don't have to remember this part, but anyway, yes. So under based on the Little's formula, you can actually calculate so many performance metrics. In other words, if you have W value only, and then you can estimate L value, and if you know the L value, and you can estimate W, right? And arrival rate is always given by your system. So that's how you calculate the L or W. Okay, and another concept, birth and death process using the queuing theory. And here's a state transition diagram. Also, yeah, we use the state transition rate diagram a lot actually in queuing theory because it is very useful to visualize the birth and death process. So here's a state transition rate diagram. So, and then all the number actually show you the state. State is what is the number of customers in the system, and arrival rate. So from the 0 customer, we have this arrival rate, and then we have so that we can have 1 customer in the system. And by having this arrival rate, we can also have this number of customer and this number of customer and so on. Okay, we have arrival rate, also service rate, right? From the disk for number of customers under this service rate, customer will leave. Actually, one of customer will leave, right? So we can have 3 customer now, and then under this service rate, you can have 2 customer, and then also under this service rate, you can have 1 customer and so on, right? So rate in and rate out usually is equal, okay? So state 1, I mean in steady state, okay? In steady state, the rate in and rate out is all have to be equal, right? So that we can make the system stable, right? Right. So if you look at this part, okay, in order to maintain the state 0, the P1, probability 1, P1 have to be multiplied by mu1 so that you can have rate in, you can calculate rate in, right? And then rate out, so probability to have this state, and which is P0, and then you can multiply this probability by the rate or arrival rate, so that rate you can calculate rate out, right? So rate in, rate out must be equal, and so on. For another state, you have to calculate it, and then another state, you have to calculate, and so on until when you have n states, right? And by the way, and this one, lambda over mu, is known as traffic intensity, which is low, and then always less than 1, so that we can have a stable system. If this value is greater than 1, that means what? You will have overflow in the system, right? You have to increase the capacity of your system, in other words. Right, and this formula is a kind of complex. Yes, so anyway, but you can calculate the transition diagram. You can compute actually the probability when the system has n customers, okay, Pn. So that's why if you use a queuing theory, even you know how many customers the system can have, okay. That's why if you can model your system using queuing theory, and that's a very helpful, but is very time consuming. So it's a kind of hard to understand what's going on in the complex system, okay. Anyway, so in order to calculate the Pn, you have to use some kind of properties, and we know that P1 equal to what? P0 multiplied by the mu0 over mu1, and we also know that this one is equal to the right hand side, all right? So for n greater than or equal to 1, right? So basically you can rewrite all the equation, and then based on this, you can get first one, you can get this kind of relationship, and then what? And change the term, right, like this, right? Because you know the definition of the P1, so you eliminate P1 from the equation basically, and something like that, and then you can do the same thing for P3 and P4 and so on until Pn, so that it will be described as a P0 function of the P0, right? So in other words, once you know the value of P0, and you can get all the probability, state probability, right, of the system, right? And we know that we know the definition of probability. Sum of all state probability has to be 1, right? That's a definition of probability. So if you add all these parts, okay, plus P0, and including this, and definitely will give you, right, start from P0 until the unlimited, and definitely you will get 1, right? And you can play with this, right? So divide this term by this term, and then you will get the P0 value here, and then you know the definition of Pn. So if you add plug in this one here, and then you can get basically the function, actually definitely the equation to get the Pn. Good? Yes. So by using that one, actually you can calculate the average number of customers in the system and average time the customer spend in the system, W, right? And once you have this, basically by using the Little's formula, you can get the W value. And then average time the customer spend in the queue. So as you know, W is what? Summation is a summation between WS and WQ, right? And since you know the WS, which is 1 over mu, and you can calculate WQ, right? So once you have W, and you can calculate WQ, in other words, right? Also, average number of customer in the queue, you can also calculate this one using Little's formula, right? So that's why in the queuing theory, it's very important to calculate the Pn, okay? So what if interval time follows exponential distribution, and then service time follows exponential distribution? Then your arrival rate like this will be like this. Very simple, right? So you don't have to worry about the individual arrival rate. So now we have a lambda as arrival rate of each state, and mu, service rate is mu for each state, right? So basically you can actually put the lambda and mu to the existing function of the L. So that's how you calculate the L value, and eventually if you use this equation, and basically you can get this, right? Very simple and easy. And then here is a proof to calculate the Sn, okay? So basically this P0, okay, equation, and as a result, actually you will get this 1 minus lambda over mu as a value of P0. Oh, sorry, yes, this value. All right, so you can use this one to get the value of L. Okay. So to get the value of L, and once you have L, and as I mentioned before, you can have other value of W, right? So L will be low over 1 minus low, okay? And W, by using Little's formula, you can just calculate the W, right? So W will be 1 over mu minus lambda, and WQ, as you know, you can subtract the WS from the W, right, to get the WQ, right? So that you can get this value as a WQ, and then every number of customer in the queue, which is LQ, will be like this, right? And this is given by Little's formula again, right? In this case, you have to put the value of WQ, okay, instead of W, so that you can get the number of customer in the queue. And then once you have these equations, performance measures, and basically you can just simply estimate the performance, okay? For example, let's say there is another case. Okay, now you know the exact value of the lambda and mu. Okay, for the single server system with the infinite queue. Okay, then you have a specific value, so that you can just, since you have the specific value, and then you can easily estimate the value of L, W, LQ, right? So something like this. So L will be what? So now you know the value of the lambda and mu, right? So that's why you can calculate the L value directly. And also we know that mu is 5 and lambda is 4, right? So if you put those numbers and in this equation, and also you can get the value of LQ, right? Once you have L, LQ, and then by using Little's formula, and you can get the value of W. W is 1 minute. So, and then WQ is 4/5, right? MM1K queuing model is slightly different from the MM1 queuing model because it has a limited capacity. So, in other words, the system can have the number of customers up to K. Okay, so let's look at this diagram. Okay, so as you know, the number in the circle actually represents the state. So system has 0 customer, 1 customer, and then up to K number of customer in the system. And arrival rate is still lambda, and service rate is still mu. Okay, so it is quite similar to the MM1 queuing model, but we have limited capacity. Okay. Anyway, so in this case, we similar to the MM1 model, actually we can actually calculate the Pn, probability of the end state. Okay, so in this case, yes, so let's look at these equations, and from the state transition diagram we know that the input rate and then output rate should be equal, right, at each state, right? So v1 times P1 should be equal to lambda times P0, right? So P1, P2, what? There's a probability of the state of n, right? So when system has 0 customer, and then we have the P0 as each probability, right? State probability, and P1 is which means the system has 1 customer, and probability of the system having 1 customer, right? So something like that. For each state, actually we can develop this kind of equations, and then since n value should be between 0 and k, so we can actually rewrite down this equation like this. Okay, right. And as you know, rho means traffic intensity, which is lambda over mu, right? And then so each in if you look at the right hand side over here actually, and you can see that each probability value is actually each probability value is transformed as a function of the P0, right? Mu P0 and mu low P0, and then low times low scale and times P0 and so on, right? And you know that we have a probability value for the k state. So now actually we can have these symbols, right? Equations. And as you know, and actually the pk also is known as blocking probability. Why? Because once system has a k number of customer, and then actually there will be no more incoming customer, right? So that's why because system cannot have more customer than the k, so pk is known as a blocking probability. In other words, whenever the incoming customer look at the k state, whenever the system has a k state and the incoming customer has to leave the system, right, without entering the system, so it's already in from the customer point of view, and it has to be blocked by the system, right? So that's why it's also known as a blocking probability. Anyway, So let's compute the Pn. Since the sum of the all state probability must be equal to 1, as you know, because according to the definition of the probability, right? So we know that all these summation of all these values should be 1, right? And then if rho equals to 1, and definitely this becomes Pn, it becomes P0, right? And if you rewrite down, if rho is not equal to 1, and definitely you can actually use this equation, okay? Right, so NA, you can actually rewrite down this equation as the equation shown here. Yes, also the equation for the Pn will be P0 times nth power of the rho, right? And same thing, once you have a queuing model, we want to calculate the value of L, and then value of the W, and so on. But when you have a queuing model, definitely you need to consider two cases. When low value equal to 1, traffic intensity equals to 1, which means input rate equals to the output rate, right? And then lambda equals to mu, right? Or when low is not equals to 1, okay? In that case, you need to use a different equation, of course. Right, so something like this. Yeah, it's a very complex, but you don't have to remember this. Yeah, I just want to explain what kind of system we have using the queuing theory. And once again, this is a simulation class, so I just want to give you the basic idea about the systems using the queuing theory, because queuing theory traditionally explains the characteristics of the system very well. That's why. And simulation is an advanced version of the queuing model, kind of. So that's why I want to explain the queuing model again. Anyway, so once you have the L value, average number of customer in the system, and definitely you can calculate the average number of customer in the queue, also known as LQ, right? So L minus this input rate, actually the over mu, will give you the LQ value, right? So basically, because now you know the L value of L, so basically you can calculate the LQ as well. And once you calculate the L value as well as LQ, and what you can actually use Little's rho, right, to calculate the Little's formula to calculate W and WQ, right? So it's not very difficult once you have the value of L, and equation is already given. So for the different cases, so definitely you can calculate just use the equation to calculate the value of it. L, LQ, W, WQ, right? Okay, so here is an example. So if you have the actual value of lambda and mu, and then now you can estimate the performance of this MM1 queuing system. And let's say the lambda equals 4 and the mu equals 5, okay? And then the k is 3. So very small system. So system only can have up to 3 customers. Right, and then as we know, the rho, initially you need to calculate the rho value, which is lambda over mu, and 4 over 5, and will be 0.8, right? Which is smaller than 1, right? So P0 will be given by the previous equation, so you will get this kind, 0.34. And then P1 for the probability value for the state 1, and then will be 0.23 and 0.27, yes. And then P2 will be 0.22, P3 will be 0.17, right? So it's not really difficult. You can just use the value of rho here, right, to get the value of each probability. Okay, and as we know, and then if you add all the probability, and then definitely 4 probabilities, and then you will get the 1, right? So now we know that this also meets the definition of the probability, right? So let's calculate the value of L, and using this equation. Yeah, it looks like very complex, but anyway, you can put the value here, right? All parameters are already given by the problem, so if you utilize those parameters, you can know that okay, there will be the the average number of part in the system will be around 1.22, right? And then LQ, once you have L, basically you can calculate LQ value, right? 1.22 minus 0.8 times 1 minus 0.17, right, will give you 0.56, right? So now you have a value of the L as well as LQ. So if you use a little formula, you can get the value of W and then WQ. So it's not really difficult. And anyway, now you have value of these two, right? So anyway, so now you have the all four performance values of all four performance measures, right? So let's compare the previous two systems, okay? And usually MM1K has less number of parts than that of the MM1 because it has a blocking probability, right? And blocking probability was what? P3, right? P3 was a 0.17, right? According to the previous problem. Where are you? Yes, here, right? This is a blocking probability, right? In this system. Right. So if I summarize the performance of the MM1Q, MM1-3, and then under the given parameter, like a C is the number of servers. So this one is 1, right? We have only one server in the system. And lambda value, mu value, rho value, still same. However, because it only allows us to have 3 customers in the system, right? This system. So L is way smaller than the MM1 model, right? And then this value is quite smaller than the MM1 model, right? And then other stuff is still also smaller than and time also, in terms of time, actually waiting time, and also the time in the system is so should be smaller than the values of the MM1 queuing model, right? This makes sense, right? Because the only system, this MM3 only allows us to have 3 customers in the system, so that's why. But MM1 model is what? It considered all possible states, right? So that's why. So it has an unlimited number of waiting line and the waiting capacity, right? So MM1Q, so that's why. Okay, and another queuing model, another queuing model. Let's consider because now you have learned about MM1 model as well as MM1K. So now we need to consider the multiple server system. So which is also known as MM1C queuing model, right? C means number of servers. So now C value is greater than or equal to 2. Okay, so multiple server system having multiple servers. So same drilling center, but now we have multiple server, which means the number of drill press is greater than or equal to 2. So in other words, C. Okay, and we have the same thing. I mean, in terms of the arrival process and then departure process and then queuing discipline here. Okay, right. Only difference is that we have multiple servers. Okay. All right. So and then since now we have multiple servers and state tradition, the rate diagram is slightly complicated than the previous model. So now you know that. Particularly, know that service rate is slightly different from the previous MM1 model. So state is still same. I mean 0, 1, 2, 3, 4 up to C, and then once we have C, and then there will be C plus 1, C plus 2, blah blah blah, right? And the arrival rate is the same. It's just lambda. However, service rate will be changed according to the number of customers or number of availability of servers of the subject system, right? So once you have a C customers in the system, and then the service rate will be C mu. However, if number of customers in the server is less than C, and then they will follow this number of actually the C minus 1 or C minus 2 and so on. So they will follow the number of customers in service. times mu, basically, right? Okay, so let's compute the probability of the end state. Okay, the system, when system having the n number of customers, right? Same thing from the state transition rate diagram. We know that each state is a, because we are dealing with the stable system, so each state should have should meet this equation, right? So input rate and then output rate should be same, right? So same thing for each state, so that you will get the probability, state probability for each state. Okay, and then change the form as a function of the p0, so that what, so that you can rewrite this equation to get the value of p0 as well as pn, right? So since so we are using the same rule, I mean same property of the probability. In other words, or sum of all state probability must be equal to 1, right? So that's why, right? Based on this property, and then you can rewrite you can calculate the value of p0 like this. Yeah, it's a way complex than that of the MMO queuing model. And then Pn will be like this. So slightly different when we have when we have the number of customer greater than equal to C or less than C. Okay, because of the availability of the server. Because in this case we have what? We have C number of servers, multiple servers. So once you have a Pn and then P0, and definitely you can calculate the LQ, L, WQ, W, okay, using these equations. Not really different. We are keep using the same property, okay? So based on this equation, basically we can actually estimate the performance of the subject system. Let's say we have two server systems, so C equals to 2, and then lambda and mu is still the same. Okay, so lambda is 4, mu is 5. However, because we have two servers, so it will change up to this state, right? So when the system has two customers, and then service rate will become what? 10 parts per hour, right? So, but currently the mu value itself will be just 5 parts per hour. So that's a slight different from the previous MM1 model, queuing model, right? And then once you have the value of the C, low, and then also the A, which is lambda over mu, okay? Now you should know that this traffic intensity is slightly different from the MM1 model, because now we have multiple servers, so you have to divide the lambda by C mu, okay? And then traditional previous, I mean the traffic intensity of the MM1 queuing model in the MM1 queuing model becomes A, okay? Let's use A for that, so lambda over mu here. So anyway, and then once you have these three values, and then you can calculate the P0, P1, P2, and up to Pn, so that what? So that you can calculate LQ. And then based on the LQ value, you can calculate L, right? And also WQ using Ritter's formula, Ritter's rule, or Ritter's formula, and then W value. Good, got it? So let's compare this case with the MM1 queuing model, and definitely because now you have more servers, and definitely traffic intensity becomes lower, that actually is lower than the previous case of the MM1 queue, right? And then L value, LQ value, also WQ should be lower, smaller than the previous case, right? Because now you have two servers, so way better, right? In terms of performance, this is way better than the previous one, right? But you need to spend more money to maintain the two servers. You got it. So here, here actually I would like to say there are multiple queuing models for the simple system. However, if you want to compare the actual estimate the performance of the system, and then now you cannot really use this queuing model because the queuing model has a unrealistic assumption. Okay, first of all, you should have certain number of servers and following the same distribution, service distribution. Yes, although you can assume that okay, server has its own distribution with different service time, but in that case you need to spend a way more time, really long time to develop the equation to estimate the performance of this system. So that's why I mean it's the in order to reduce your time and effort, actually it's better to use a simulation to analyze the performance or estimate the performance of the very complex system. Okay.